hardware and software verification. So you can actually verify things about chip design because they are actually quite clearly specified.
Most podcasts talk to founders after the story is already written. When the latest raise is announced, the product has shipped, and the narrative is clean.
We wanted to find out why they decided to take the founder leap in the first place, what idea captured their imagination, and how they handle the pressure to build. Welcome to First Commit. I'm Laura Hamilton.
I'm Eliya, and we're investors at Notable Capital. We spend a lot of time with technical founders who are on the cutting edge. If you're thinking about what it's like to start a company in the AI era, this one's for you.
This is First Commit. Let's get into it. Today, we are welcoming Carina Hong, who's the CEO and founder of Axiom, building the AI mathematician. Welcome, Carina.
Hi, great to be here.
Excited to hop in. So let's go back. You're at Stanford. You're young. You started a company that has already raised over $200 million 15 months ago. What did you know in March 2025 that made you sure it was the right moment to start Axiom?
Yeah, I think March 2025 was an interesting time, just in general in the AI landscape. We are about 6 months after the first reasoning model launch, OpenAI's O1. We are more than, we're more than 2.5 years after Lin 4, which is the programming language that we depend on to do math proofs. The latest version, Lin 4, has been rolled out in September 2023. Am I calculating right? I think it's roughly. Oh, it's 1.5 years later.
We'll plug in an Axiom.
Yeah.
It'll give us the answer.
It's kind of an interesting sort of intersection of time between kind of the reasoning model's capability, or not just sort of informal reasoning, but also coding, as well as formal math development, making Lean a lot less finicky and much better suited for industry scale engineering. So those three things I think are happening at the same time. It's also a time where people are feeling pressure, I think, from various big tech places to play catch up. So there are a lot of, I think, efforts and initiatives to try to train close to frontier models, but didn't actually necessarily pay off. So a lot of churns at big places. So talents are starting to float. There was no new lab at the time. I think the ones that we know of at the time were Eliya's SSI, Safe Superintelligence. And Miro was, I think, still starting to raise or just close around, something like that.
A lot has changed. So I'm sure our listeners are familiar with reasoning models and chain of thought one and the whole evolution, but maybe much less familiar with Lean. Maybe you want to share a bit what Lean is and how it came to be.
Lean builds something called type theory. It has a lot of objects, each have its type, and they're like logical dependencies.
So not TypeScript.
No.
Type theory.
No, type theory.
Okay.
TypeScript is actually kind of on the other end of the spectrum. It's dynamically typed language, so it's quite hard to deal with. Well, actually, no. TypeScript is statically typed versus JavaScript is dynamically typed. So Lean is this sort of formal language where you can write math proofs in. You can also do other things in Lean, like you can build an autograd in Lean. Nothing's stopping you. So it's a functional programming language where you can do various things in, but you can also write math proofs that become computer programs where you can execute. So once you execute it and you see a check mark, you can be pretty confident that the statement that you asked the system to prove has been proven. Now, obviously, if your statement is wrong, then there's no guarantee. So people still need to check the statements. Compared to, say, 3-line, 5-line statements versus like thousands of lines of proof, you're definitely making the work a lot better.
So a way to think about it is a proof compiler of sorts.
In a way, yes, that's right. And it's developed in, I think, 2013, 2014 by Leo DeMora and folks. He was at Microsoft. It was a great nonprofit, the Lean FRO.
Very cool. Thank you for that.
Can you just touch on the broader vision of Axiom and where you guys are today?
Back to March 2025, it's like these three things are coming together. There has not been an industry scale effort to make AI for math a reality. I was seeing Google DeepMind doing work on math Olympiads. It was also at a time where I feel like that effort has kind of ramped down. There are kind of efforts starting in China, DeepSeek and ByteDance, but it wasn't very clear that geographically that's going to work for me personally. And so, yeah, I think I wanted to start this effort to make AI for math discoveries a reality. One thing I was very much insisting on is research math. That has to be the priority and goal beyond Olympiad math benchmark problems. Because the thing is, if you think of Olympiad math benchmark problems and the role they play in a lot of models' eval, by, frontier large language model. There's so many benchmarks there. There are like even like a healthcare benchmark somewhere. There's RKGI that shows reasoning and superintelligence. And there's nothing sort of special about math. And for me, math is really special. And for the people that later joined Axiom, math is very special. It is the fundamental of a lot of scientific domains. It can be expressed in code and by the Carter-Howard correspondence, and for the existence of Lean and other formal languages, like other versions like Isabelle or Coq. And math and code can control a lot of scientific domains, and you can run experiments about the physical world, and you already have reward. You can control reward. It's a reward kind of flywheel compounding. So math is very special for us, for our personal passion reason, and for these reasons. And just like I believe, for example, Anthropic believes in coding is going to transfer, we also believe that math is going to transfer. So that was I think, the initial spark vision in March 2025, which is, and I was very sure it's going to happen. I was like, by 2026, late half, we're going to have AI prove at least a research math result. Turns out that's way earlier. I mean, beginning of the year, we wrote out 7-8 papers now on archive. 2 of them recently got accepted to professional math journals, Archive de Mathématiques and Inductionnis Mathématiques. So we have seen instances from Axiom Prover and also from Google DeepMind's Eliya agent, and also amateur mathematicians using frontier models. In all 3 cases, prove a lot of research results in math.
Carina, maybe you can walk us through a bit. What do you think is wrong with current AI systems and why they're not good enough to do formal math?
There's this belief, I was chatting with someone who works in private equity, that AI is their partner. And they also, I think, don't like Excel now. So it's like they're at an interesting point, right? Where you see all these like AI for Excel companies. They don't want to do Excel. They don't want to reason in that abstraction. They don't trust large language models output. Even the coding models, which I think have a lower chance of hallucinate, I think it transfers that way, are still hallucinating when it comes to math. And we're at a point where we feel like there's so much need for something that can be a thought partner, but can also give like actual correct like conclusions, quantitative ones. I think that's kind of the future we're kind of starting to see. And I know that there's a history toward, okay, well, if you want to kind of try to formalize language, you're going to hit this roadblock. And the other one, Chomsky has all this work and attempts. And other people were also trying to do like full stack language, I think since like 1980s. But we're finally at the point where I feel like the intersection of them is the reality. I mean, it is not purely formally verify everything because we'll all kind of wait until the end of the universe. It's also not like wipe coding to the end of the universe because then you're going to see blow up at some point. The reality is somewhere in the middle. I think current AI lack the ability to consistently, reliably give you the correct output, and their value in getting that, or not making the mistakes or catching the edge cases. There's another additional layer of value of trust that you can actually deploy that output. And I think people who are working, for example, AI for science, looking about like for them like the decision to go into like actual physical world like experiments, very expensive and costly, and a lot of theoretical level stuff needs to be like 100% like soundproof. And I think those are the realities we're seeing. And if there is a technically plausible solution, actually with not much technical risk because it's proven, that is where we should go. And that's kind of where we want to go next.
To help conceptualize this a bit, walk us through. So Lean is this project you're using, but help us understand how Axiom's own model fits in. What's the interaction model? Lean is the substrate, and I'm sure reasoning comes a lot in. The feedback from Lean serves your model as a reasoning layer.
Yeah, so Axiom Prover is a system. It's an ensemble of multiple models. Some are informal, some are formal. There are a set of tools that we have open released called Axiom Lean Engine. We rolled it out, I think, like about 8 weeks ago in March. And people around the world have been using different kind of AI theorem proving models on top of Axiom infrastructure. And this whole system, the models underlying it trains on like Lean data, which are math proofs written in Lean, the programming language. And so therefore the system can take any natural language questions and produce a Lean proof which to me at the beginning felt like magic. I mean, this is magic because of a few reasons. One, everyone was telling me that data is really scarce, right? You're functioning in a data scarce domain, which is could be a reason why I say like the frontier labs are not doing it, because they have a lot of compute. They will have much more of a strategic advantage to play in the data rich field to utilize those compute. And one is data scarce. The other one is that just it hasn't been shining in the math Olympiads before. You always see the informal models are like really crushing the formal ones. I think that was a lesson people learned.
Maybe quickly explain the difference between a formal model and an informal model.
So informal model is a model that produces output mostly in natural language and when asked to do math in the specific context. And a formal model is one that when I give you a math question in natural language or Lean, it gives me the output in Lean, which you can be sure that it's 100% correct by simply running the program. Interestingly, you don't need to understand.
Once it's translated into a formal format.
Yeah.
And you can't do this today with the current models, like foundation models, because they're not the capabilities.
Yeah, people find general purpose models to be lousier Lean capability.
So an example would be like, not in math, just to simplify for our listeners. So let's say I'm designing a system and in simple language, I say, it's a payment system. I want to say, never pay twice. It's a bank transfer system. That sounds very intuitive for us as humans, but as a system, it might fail at the database layer. It might have network, a timeout, a user might be clicking too many times. So Lean would translate that natural language statement into a set of clear requirements that then can be proven in a formal way.
Correct. So there are obviously nuances to that. So for example,
of course, we're simplifying it.
Yeah. But in a lot of the cases that we observe is that if you have the specification in mind, which is the things you want to verify, in this case, never pay twice, it's proving is, which is Axiom Prover's job, becomes a lot easier.
Yeah.
Right.
For the set of these statements, the following claim is true or not true.
I think that Axiom Prover has surpassed a level of reasoning ability, formal reasoning ability, that if you give me clear specification, I have a high chance of proving it. If I don't prove it, you would not be misled into thinking that it is correct or satisfied. But if you don't give me the specification, you say, I want this to be safe or good.
Yeah.
It becomes a lot trickier.
How do you envision people using Axiom? Or is it you're always on math copilot?
I think that will be a very interesting sort of like, first kind of research, product. But the general sort of domains we're trying to go in are hardware and software verification. So you can actually verify things about chip design because they are actually quite clearly specified, right? So for example, I will never want a race condition to happen. Or I want to make sure that, not certain kinds of components are full at the same time, because otherwise that's assumption. All these things are already presented as clear specs. And with those specs, we could try to have Axiom Prover generate. Now, there's a little bit of advantage of that versus existing EDA tools. In that existing EDA tools, a lot of them rely on something called SMT solver, which is Boolean logic. And it can get very high complexity very quickly because you're exponentially,
the state space becomes ridiculous.
2 to the x is probably your like lower bound, right? And that becomes quickly unmanageable. And this will not happen with Lean. And in the case of software verification, we're seeing obviously being a more messy domain than chip verification.
Just because of the abstractness.
Yeah, people like safe software, like you don't know what that means. But in a lot of places, actually a large amount of high complexity industry projects in the B2B world, they do have specifications, right? They want to make sure that there's no security loophole. They want to be able to formalize, say, a hypervisor as a certain component instead of humans, right? Like
you want to have some sort of cryptographic assurance about some whatever workload or transaction.
Exactly. Yeah. So I think those are the starting cases, which is that everything you can define, you can execute. And just like that, everything you can specify, you can prove it.
It sounds like there's a lot to do with this.
Yeah.
It also, my guess will be, we're a bunch of nerds in this room, but most people, this is a bit too abstracted for them. You had this intuition in March 25, and one was just coming out, and Lean was already there. I wonder, a lot of the applications, was that something, the use cases, is that something you had in mind prior?
No.
or it evolved over time?
You see, I personally don't. I have the ambition for math. I want like scientific breakthroughs. I was so excited. I was like, I remember it was honestly like I had to start this company because I already couldn't do anything else. Like it was a state of almost like total consumption. Like I mean, like
Paralysis.
You're high on your own
I
supply.
am high. Yes, like I was just like so confused about. I've never seen this state of me like before. I mean, like maybe if I'm crazy about a boy, like like that sort of in love with the idea, like being totally like just obsessed with that. And
It's addictive,
I
huh?
was like, well, I mean, I'm not gonna be productive any other way. Like I
You
might
have
as well
to.
just do that. Yeah, but the other people who join my team, they have that vision. I think a lot of them are industry veterans. Some of them have been doing software testing. My really good friend and CTO, he did software testing work all across the work of Stanley, all across Meta. And there are other people who were doing chips for many years. And there are people who did chips and then go into formal methods and then go into reinforcement learning and thinking about the combination of formal methods and reinforcement learning, right? Like these people, they have these other sort of application areas in mind. I was thinking a lot just about math, and I also did, I think, a bit of, experience at XTX, which is a really, really great quant trading firm. So I did some math there. So I thought math has to be making money. It has to be useful. Like it just first principle wise.
You've brought in these individuals who have a lot of experience. How is it for you leading this organization? Where do you find that you need to set the tone, and where do you take a step back and allow others?
I think we have very good research taste as an organization as a whole. When it comes to research taste, that's where it's something you just have to insist and you cannot get it wrong. And research taste
Can't be formalized.
Yeah, it's hard. It's an art. I think research taste, there are consensus by the community, especially great ideas coming from academia communities. And I actually attend, I think, a lot of conferences and discussion seminars. And those are things I love to attend. And I think I'll bring that taste back. And also we share papers. I mean, it's a very, very researchy organization. So that's where I would have a very strong voice if I feel like the research taste is diverging from the ground truth. Where I take a step back is, more on the, I think, execution. Like we have really great world-class engineers and they have sensible plans about where to go. And I will just, let them cook. And it's also, I think, an interesting mix of, you mentioned there are experienced folks, but there are also some other very young, high agency folks with very good discipline and training in a way. Like as in like they're very good coding machines and they are very good system designers and they know the info like in and out. Those folks are also very important, I think, as a complementary to the more research scientist vibe of folks. And we try to have full stack folks, but sometimes I feel like that is also a very important piece.
You touched on taste a lot, and I feel like that's your unique charm probably that you bring. Do you feel like that taste is the unifying substrate between these different types of individuals, and maybe it's the first time for those people working with different personas?
I think there's taste and there's optimistic taste. So this is a very, very interesting concept. I think as founder or CEO, considered chief energy excitement officer.
I want that title.
Yeah, you want to bring that taste away from anything that is not constructivism. So, there are a lot of nuances, I think, especially by experts about what is not possible, what is not possible. That is hard. That is obscure. That is difficult to define. And so what is the can do? Like, what can we do? Like incrementally, right? Even. And where do we know, like, critically, where are we aware of the boundaries and within that space, how much we can push. And I think that is something I feel like having higher agency folks really help. I also think that people who come from, AI versus formal verification, the CS people versus automated theorem proving, the non-AI AI for math. Well, the non-AI, I guess, like machines for math, like, automated theorem proving people and the lean people and different, substreams within that, like math lit people, meta programming people. They all have their sort of like know-hows. And sometimes they don't speak on the same language. I don't think it's the taste diverging being the challenge, but more like the terminology and language diverging being a very clear initial barrier. But then once that is solved by good kind of coordination and communication, good culture, once that translation is done, then the taste becomes actually a lot. I actually find it beautiful that the underlying taste, as in the optimistic part, are converging. This is the nice thing I think about doing research. This is a fun part of my life. Is that you see the same thing you can borrow from other literatures that can be applied here. For a long time, I would go into James Stowe, who is a Stanford professor pushing AI for science. Not necessarily they're improving. I would go to his lab and just look at the papers and take ideas to math. I mean, this is like a source, a stream of ideas. And the other stream of ideas, I look at the hypothesis generation, how people generate hypotheses, and then AI experiment and try to have AI submit to ICML and those like machine learning paper. I also borrow ideas from there. And Shubho is a visionary as well, and so on, and Ken, a lot of our research scientists and folks. I think that we are very clear on AI for math is just a starting point. And I say that not just in the verification being the best first market sense, but in there's so much to be done on self-improving reasoner, where we need conjecturing to fit with proving, where we need auto-formalization as a way of hierarchical planning, honestly. Auto-formalization refers to converting math in natural language, like English, German, French, Chinese, to lean. And auto-informalization refers to converting it back. And we believe auto-formalization, auto-informalization forms a bidirectional circle between different abstraction. And it is a way of hierarchical planning. It's a fundamental technology, not just to generate data for proving model, but as crucial, important, and maybe even at times harder than proving, because when you're auto-formalizing the statement, you don't have the reward. So these are, I think, things that draw also talents to Axiom, because they see these sort of hot takes and they're like, well, that is actually a grounded way to think about things.
A lot of times how taste comes out into the world, hot takes.
Yeah.
How do you think, as you're recruiting and building a research-oriented company, how do you balance product and research? Because at the end of the day, you have to make money at some point, but the research is the core of what makes the product incredible.
We currently have our core research engineering folks working on some very important future customers' cases, like just directly. So there's no sort of separation so far. At one point, we might need to consider, having product engineers, and it will be kind of a little bit different sort of composition of the team. But currently, what we are really seeing is there's a lot of capability overhang of our Axiom Prover technology, and we try to go into these domains where we want to pursue and learn from the experts there and try to see how we collaborate. And it's actually surprisingly working well when you have people who are nerds to try to sell to nerds. And we find that to be working quite well for our early stage.
It's not B2B, it's end-to-end.
Yeah, it's funny.
We ran into math a lot. You talk a lot about taste. Something I've always been explained to me that's beautiful in math is how can you prove something with a minimal set?
That's right.
That is what you're describing
so
right
you
now.
can prove from the fundamental axiom that 0 multiplied by any number is 0. I was asked to prove that when I was like, I think 15. Like I was like, well, of course, like 0 multiplied by everything is 0. And like to prove that from those axioms was fascinating. Like, and it really rewires my brain, I think, back then about how I think about things. And then the same way I go all the way to quadratic reciprocity. So I go from there all the way to quadratic reciprocity, where I don't take anything for granted, just one by another. And it's fascinating. That was fascinating to me, the deductive nature of things, deductive logic. And I think there's this other thing that was fascinating to me is how things magically connects when you have mirror symmetry or things that are coming from theoretical physics. You can try to do it in math. Even in now AI for math methods being applied on AI for theoretical physics. I was at Stanford for Human AI Institute yesterday on a panel with Professor Kyle Kramer. He's from the same sort of, I know him from François, and because of their collaboration on having how a transformer would predict call-out sequences, which is a pure math problem. The underlying technique, the same technique, it can predict the coefficient of the amplitudes of the Young-Mills theory, or something of deep interest to theoretical physicists. And I think they're submitting a Genesis project together. And those are fascinating to me, how things connect, have both real-world implication, but also it's a bidirectional discovery. So sometimes physicists bring their thing to you. Sometimes you do something and think that might be related to, say, particles. It's bidirectional as well. And ideas fuse more, I think, now with AI between the different scientific subject, but it doesn't flow in random direction, right? You could argue that you need a theoretical layer for experimental subjects. And I did 1 year, this weird year in neuroscience where at least half the year was in AI. So very, very brief time there. I remember when theory of neuroscience and by various methods, some computational, some just mathematics, honestly. It's like you have actually equations and stuff programming it. And how that kind of converges with the experimental side of things. And that is, I think, what neuroscientists consider beautiful. I think that is another property why I think math is beautiful. Yeah, it solves these problems. But the problem is most mathematicians don't talk to applied scientists enough.
Yeah, it's easy to get lost in the theory and not understand where it can be applied.
I mean, for a long time, didn't know the definition. I didn't know the definition of DNA and RNA. I mean, like, and then to go deep into a field of neurobiology, right? Like, it takes a lot of the translation there.
Mm-hmm.
But if they have an AI mathematician, I think that's going to be interesting. The shocking result I saw of MIT Eliya Feat's lab is Chinese remainder theorem, which is a rudimentary elementary number theory result, was used to calculate how neurons space out, like the neural capacity. So you just think that if you give all the applied scientists Axiom Prover, like how many more things can be discovered on the theoretical level, and how many of them will find experimental grounding. And that's, I think, when things get really, really like weird.
You think we're going to see the equivalent of vibe coding with a vibe science?
I don't know. The 2005 Nobel Prize finding, grid cells, place cells, they file in like honeycomb, hexagonal, six polygon patterns. You have a math proof. You have people who give a math proof for that. It's something about minimizing the energy spent. It's fascinating to me. In that case, it's a proof, right? We want AI where it can conjecture. That's going to be freaky. I mean, it's like the math intuitions, which is captured in both the act of conjecturing and in a lot of the cases, the pre-conjecturing, just like you're starting to see patterns and you're not sure how they fit. And you see something that don't fit the pattern, but you believe they are non-important. You have that optimistic taste because, you're going to have your conjecture. You have to ignore some of those weird, initial rebellious patterns. And that process, if scientists can have that, I think that's interesting. That's why we're, focused on not just proving, but also constructions, right? AI for finding outlier constructions. And this is called discovery, the discovery line of work, which are not related to formal theorem proving, but they should integrate and they should be one workflow, I think.
This is all super fascinating. And Axiom is clearly on a beautiful path of success right now. But I mean, and it will fundamentally change what it means to be a mathematician. But when you think about it evolving, what is the potential resistance you foresee happening?
Resistance happening, I think, one, we are in a little bit of a crazy market right now in terms of both, I think, the labor market. And if you have a lot of heat in the market, then fragmentation of a field is a very natural, probable consequence. So why would someone join a company? You will all start companies. And then this field will have 1,000 companies and nothing gets done. All the time is sort of spent on the initial co-start activation energy. That's one thing I worry about, I think, in terms of resistance. And also, I guess, comes to that, right, which is that you need to execute very, very fast and really compound from there otherwise.
I think that's an important point, and I think it might be relevant in other parts. I just want to make sure we understood you. So your point is capital is so available.
Yeah.
Anyone can start a company. But in order to solve a really hard problem in the world, you actually need people to commit to a cause, not fragmented into thousands of causes.
That's right. And I think that's how you tell categorical. So if you see a field with way too many attempts, and like if you look at the probability of like what is the expected number of good researchers in the field,
maybe we'll formalize here a property of a bubble.
Yeah, I would have a theory on that, right? And that is potentially helpful to friends as VCs, right? Like you can call that fragmentation index of a category. Right, you estimate the number of good researchers from there based on a couple of factors, like how new the field is. Does it have an academia history?
Strong assumptions on the scarcity of the category. Yeah.
Yes, and it's not just, I think, starting companies. When I mean capital is available, we also see sort of the pay packages of big tech being quite interesting. And sometimes you buy projects to kill it. which I find that to be not in favor of constructivism, right? And the whole concept of constructivism, as Richard Posner's famous judge who loves math put it, there's certain economic activity like locks. If you build a lock, you're preventing your neighbor from stealing from you. It doesn't create economic value. It doesn't grow the pie. And there are certain other economic activities that are constructive, which means growing the pie and you create value and then you capture value. So I think there are certain sort of phenomena we see in the market dynamics that are not necessarily for constructivism.
Do you think there's limits to what can be formalized?
I think so. Yeah, of course. I think that a lot of the word is still fuzzy. And I would note that a lot of humans have the best intuition about data. This is really, really freaky how good we are to see outliers in data. And we're trying to solve a little bit of that by pushing on the discovery work stream. But that is something where I think human intuition really trumps right now. There are cases where there are obviously a lot of formats of data, right? I think because time series and its implications in trading and the whole art for trading literature, that's understood a lot more by AI. But the other, I think, fuzzy thing is just there are large parts of, language. I think of language as a manifold. It's a high-dimensional manifold, and it has distributions around words. And math or code, actually each programming language, it's weird that I call math a programming language. And there's this sort of very provocative line of math is one of the last programming languages we haven't conquered by AI. And it's a sub-manifold of that where the distribution changes rapidly. And a lot of these sub-manifolds, say in the family of formal languages, say in the family of broader programming languages, they have similar distributions where you can expect transfers. But there are a lot of other parts of this high-dimensional surface that are not related to these family of sub-manifolds. That's how I think about it.
Interesting.
Awesome. Well, thank you, Carina.
Thank you.
This was so much fun.
Yeah, it was fun.